Does the cleaner combustion of the United States and of Europe release whiter particulates that reflect more than the oil-based two-cycle engines of a lot of Eastern Europe and India that have a darker particulate?
Well, so carbon-based particulates tend to, Brian's probably should answer this better, but there's the carboniferous-based particulates which absorb radiation and then re-emit it. They still block radiation from the surface, but then there's the sulfate aerosols, which are this whitish haze that you see if you look out an airplane window when you fly across the United States. And that comes from sulfate, burning of coal, essentially, and it's pervasive. But initially it starts out as sulfur dioxide. It gets oxidized, so it's a gas. Mm-hmm. Then it gets oxidized and forms this little tiny particle, and that is reflective. And so that does tend to produce a cooling effect.
So there are several ways to think about the particles, and a lot of people like to talk about something called radiative forcing from these greenhouse gases, which is a few watts per meter squared for the greenhouse gases, compared to the solar energy, which is 300 and something watts per meter squared. So in the first place, all these climate effects are being driven by something as below 1% in energy balance of the Earth. The aerosols in the atmosphere have a radiative forcing that's well above the greenhouse forcing. So they're forcing the climate. I'm not talking about clouds. So greenhouse gases are a couple watts per meter squared. Clouds, are probably about 40 watts per meter squared, positive, and bigger than that negative, which balances out to about 20 watts per meter squared negative. So clouds are 10 times more important than the greenhouse gases. So any little perturbations in clouds will overwhelm the greenhouse effect. And aerosols, not counting clouds, are also much bigger than the greenhouse effect, but most of them are natural. They're like windblown dust or sea salt or something like that. So picking out the people part of that is a little difficult. However, the anthropogenic pollution in about a week, 1 week's worth of aerosol pollution is equal to more than 100 years of greenhouse gases. So the aerosols, we're actually kind of vulnerable to the aerosols because they have such short lifetimes. So if you shut off the production of them, since they're currently balancing out some of the greenhouse gas stuff, you can make a whopping big increase in the positive warming because the aerosols are actually causing an effect that's fairly large. It's opposing the greenhouse effect. They have a very short lifetime. They're easy to get rid of. Carbon dioxide is very interesting. It's something that I think IPCC hasn't done a good job of explaining. So people talk about lifetimes a lot. So there are many things that in a few lifetimes just totally disappear. Like if you have a chemical and it chemically reacts, it goes to nothing in a few lifetimes. However, when people say CO2 has a lifetime, it's not the same lifetime. It's an equilibration lifetime. It's really the time it takes to go into equilibrium with the oceans, and it does not go away. So if you actually want the CO2 molecules that you put out now to go away, the time scale for that is probably like 100,000 years. So we're dealing with something here on geologic timescales. The molecules you put in the atmosphere of CO2 are not like the sulfate that you put up. The sulfate, a couple of weeks, it's gone forever. That CO2 is around for a geologic lifetime. It won't go away until it gets converted into limestones in the bottom of the oceans, which is going to take it a geologic lifetime. So I don't think people understand that people are messing with the Earth here on a geologic timescale.
Kevin, do you want to add something?
Well, weathering of rocks is one of the ways in which you can take carbon dioxide out, and that's certainly geologic in time scale. And a lot of carbon dioxide goes into the ocean, and it's actually acidifying the ocean to some extent. But one way in which carbon dioxide can effectively be removed from the system is through the little organisms that are in the ocean that form bones and shells. That's carbon. And when those critters die, they fall to the bottom of the ocean floor. They get embedded in the sediment, and then they're effectively taken out of the system. And so that is maybe a little bit faster process, but